So let me start. So I'm an engineer by training, and my point is to see if things that have a great promise can be made practical and can be made useful on a global scale. And we have been quite successful when it comes to video compression, and so we are trying to carry this over to other topics. And I will talk about how we are trying to make AI, machine learning, which we see as an algorithm that is useful. And I think that in a couple of years, maybe you will hear of other algorithms that are useful, how we can use them to bring them into relevant engineering and other problems and make it scale on a global scale. So I'll talk about machine learning for communication and health. So it's really two parts of the talk, but the basic idea behind it is similar. First, some shameless self-advertising. So I'm heading the Heinrich Hertz Institute in Berlin. We are globally active. We do machine learning, video coding, computer vision, wireless, and photonics. And our claim to fame is that every second bit on the internet touches either our video or photonic technology. So the outline of the talk will be two parts. So I'll talk about machine learning for communication, meaning video compression. And I'll talk about machine learning for mobile communication, and in particular 5G and how it's going to be relevant there. And then the second part is about health. I'll talk about some best practice examples shortly, but also talk about the focus group on artificial intelligence for health. So let me start with the communication system. This is a very classical picture, and I'll basically talk about two parts of it. I'll first assume that the transmission system works perfectly, and so I can basically make a shortcut here and talk about the video encoder. What does the compression system do? Well, for instance, in the HD signal, it's about 600 megabits per second. Let's say this is 100%. It squeezes into a pipe of 10 megabits per second, and that still doesn't sound impressive, but if you look at the percentages, it's 1.7%. And then it reconstructs the HD video, and you are then again at the 600 megabits per second. Hopefully it looks good enough for everybody to watch. And this is kind of used everywhere across all transmission media, and it's viewed on many, many displays these days. And 80% of all the bits on the internet are compressed videos, and H.264 is the vast majority of this, and now H.265 is catching on. So the principle is that you have video signals, and they are a sequence of pictures. And so what you do is you process them sequentially. And for instance, if in the current picture, and let me just show you my animation. Yeah, so you are searching for a block that tries to match this one. You find the right one, and then you compute the difference between the two, and the difference is easier to code than what you're currently doing. So you compute this difference, and but the whole thing is actually more messy than you think. For instance, there is this part that you can't predict from the previous, so you have to take another one. And then the whole thing is highly adaptive to the video signal, and again it goes on and on and on. So the first video codec description, H.261 in the 90s, was 25 pages. And it went on. So I wrote H.264, and I delivered it, and it was actually, I got an email back when I delivered it that morning. You got to be kidding me. I said, why? I said, well, it's 264 pages. So it was 264 pages, H.264. And H.265 was about 600 pages. So you can see how much more complex they are. In fact, they are so complex, these algorithms, that the product space of all the options within the upper left corner of the picture exceeds the number of atoms in the universe, which is estimated to be 10 to the power of 80. So you can easily tell this is a problem that is unsolvable. So what we have done is we have basically used machine learning for it. We trained on natural video signals. We used the codec syntax, and we used the boundary conditions. And we trained a machine learning algorithm that itself produced a video encoding algorithm. And that actually was quite successful. I'll go on to the second part and then show you where it's used. So the second part of our compression system is now this person here. And the visual perception has been a huge topic. Again, you might think visual perception is something that doesn't affect you. Well, it affects you quite a bit. If 80% of the bits on the internet are videos, and you are watching them, and humans are watching them, then the perception of distortions in those videos, because they are heavily compressed and you have distortions, almost nobody in this room has seen an uncompressed digital video signal. You just don't get to see them. It's very important to understand human perception. So, the traditional video coding setup is that you show something to somebody on the display, and you ask them questions, and they will give you a subjective assessment. And you do this for enough people, and you average the numbers, compute confidence intervals, and you get to your assessment of the quality. Now, I would say we need more brain in video coding, because in reality, the following happens. The optical signal travels through the optical system of the human. So the cornea, the lens, the retina. Then it goes through your optical nerve to the back of your head, and it goes into your visual processing system, V1, V2. And then at the end, there's your decision point, which is up here. It's a marker called P3, where you come up then with your subjective assessment. About 1/3 of the visual cortex is used for visual processing. So it's the evolution has taught us that that's one of the most important tasks that we are fulfilling. So we can actually go ahead and measure this processing or parts of it and try to make predictions. So what we've done is we recorded EEG signals while people were watching a video signal. And we found a method to actually extract the quality they perceived from the signal. So here's a very sketchy way of looking at it. So we actually managed to relate compression levels to measured amplitudes. We did this for patches of the video signal and basically could derive a measure patch by patch for the video signal, how the brain perceives the distortion for these patches. We would then implement this into the video encoding algorithm, which is based also on machine learning, and that way achieve better subjective coding efficiency. Why is this better than having people just look at it? Well, if you have this video encoder, and I showed you these small blocks, you have to make a decision block by block what to do. And you need basically guidance block by block what to do. And this guidance is given to you by a model that is to be derived for these small blocks. But some blocks don't have a meaning for humans. And a distortion shown to them doesn't matter. But we need that distortion sensitivity for these blocks in order to actually be able to run the encoder. So here's an example. I hope you can see it. So there's a soccer player down here. It's probably very difficult to see. Basically, same bitrate, and it's highly improved. One of the reasons is the contrast is lower for the lower part of the soccer field, so we basically assign less bits to it, and the soccer players look bad, but people will realize it once they look at the lower portion of the picture. So we basically went live with this in 2016. It was actually in Germany, Sky. It was this game, Dortmund against Berlin. Berlin's my home team, which hasn't been doing so well, but that one ended 1-1, so it's okay. The second part about communication I wanted to, and then the last thing is, so H.265 has seen a rise this year by 28%, but we are now working on versatile video coding. It's just a sketch, so we want to, again, come up with half the bitrate for the same quality when it comes to video compression, and that by 2020. So let's talk about the second part of the communication system. So we just assume compression works just fine. Actually, it can't work perfect, at least from our current understanding, but that will be a different talk. And we'll talk about the transmission system. And the most important kit on the block is 5G. Well, what you can see here is a plot of different KPIs that you would assign to a transmission network. So traffic capacity, peak data rate, user experience data rates, spectrum efficiency, mobility, latency, connection density, network energy, and we would basically see how 4G actually fulfills these KPIs. And the aim for 5G is actually to have something like that, to be good at it everywhere, but the most important thing, not at the same time, because that is physically, at least from what we know, not possible if you limit the resources. So we would basically be looking at ultra-reliable and low latency communications, and this is the basis of the tactile internet, which is the idea that you put control loops into a communication system, meaning a car or a robot that is highly connected with the infrastructure. It's being controlled by the infrastructure that requires ultra-low delay communication. Cars that drive in a convoy very close, they are synced up through communication, and they have to be reliable so that when the first car brakes, all the other ones are braking. And you would basically be just looking at those KPIs there. And then we would talk about massive machine type communications, which is the Internet of Things, which has different KPI requirements. And then we would talk about, lastly, enhanced mobile broadband, which is kind of the extension of the 4G versus 3G model, where you just have more bits per second. But it's not so latency sensitive. Now, if you are a mobile operator, and you need to do the 5G investment, you have to figure out what to do, because this is going to be expensive. And one way of doing it is if you try to implement the enhanced mobile broadband, and you put some extra money on the side or extra investment on the side to enable the other features, like the tactile internet, like flying drones through your network. Where does this lead? Let me sketch out where does this lead. So, first of all, we want to have 1,000 times the throughput, right? That's what the enhanced broadband is aiming for. And we can write 1,000 as 10 times 10 times 10. And we can look at it as, so the throughput is defined as bits per second per square kilometer. And we can expand this by bits per second per hertz per cell, and then cell per square kilometer times hertz. And by the way, this is the same hertz as Heinrich Hertz in our institute's name, but that's just a coincidence. Spectral efficiency is the first factor, so we can actually beef up spectral efficiency using massive MIMO technology. We can then use small cells. That, in fact, means we can use every light post, every traffic light will become a base station in 5G. And we can also go to higher, use more bandwidth. So we would then, however, have to go to higher frequencies. And this leads to a new 5G architecture. So how does this may look like? Well, a little sketch. So first of all, we would split the control and user plane. So we would go ahead and we use, for instance, the 4G infrastructure to basically locate you as a user. So you're basically in this big cell, and there you are. That's the first thing. But then you would get the data through those light posts or through the traffic light. And we would be doing this through a massive MIMO antenna. The massive MIMO antenna is an array that through software can be configured to create a radio beam heading towards you. And we would need to have line of sight to be effective for this. So we would have this massive MIMO antenna, for instance, at a building. So it can be part of architecture, these massive MIMO antennas. And then you are moving with your car, and we need to predict where you go. So that's the first machine learning task, to figure out where you go, because we need to track you. This beam has certain characteristics in order to be effective when it comes to data transmission. For instance, there's a bus in the way, so we have to be smart about that aspect, so anticipate it. And so we would basically transfer the data to other nodes and predict then a capacity map. And all of this done today is through machine learning. So what happens is this more complicated network architecture, which requires this line of sight to get to you these 1,000 times the throughput than 4G or LTE, requires all this data processing in the background to be smart and to be effective. So if you look at it, machine learning in the context of 5G is used, for instance, for mobility pattern prediction, end-to-end network slicing, IoT edge computing, RAN feature extraction and compression, deep learning, caching, and many, many others like handover, load balancing, channel modeling, prediction, self-healing, link adaptation, and so on. So therefore, we have one of the steps to take it mainstream is we have created a focus group in November last year. It's called Machine Learning for Future Networks and 5G, and it's open. You can attend, no charge. It's open to everybody. And the next meeting, the last meeting was in Santa Clara at Intel. The next meeting is in Tokyo in Japan, 26th to 29th of November. And you know, if you're interested, please go there. So this is the first part of my talk. So I'll now move on to the second part. And I remind you, so I want to also talk about health. We have actually done quite a few projects, and my colleague Wojciech Samek should be somewhere in this room. He'll talk about them, and in particular, he'll talk about explainable machine learning later. So we worked on EEG, I told you earlier, but not only for visual perception, but also for health issues. We worked on fMRI, histopathology. We did gait analysis, limited angle tomography, dynamic MRI, ECG. We actually are currently estimating, we're predicting strokes from ECG, and we are combining it with a transmission system in order to also remotely do this and be smart about it. Proteomics, where we try to analyze proteins over sepsis and robotic surgery. So we had all these projects. And I think you are aware of many other health projects for that use machine learning. The problem of them is they are kind of all just projects. They are, and same for our stuff. Just we do this, it's fine, we have our data set, we come up with results, and it looks fine. But how can we actually take our ECG method and make it global scale? How can a doctor in India say, I'm relying on this German ECG stroke prediction method because I want to use it, because I don't have time to look at the ECG all the time. I need just an alarm to then attend to the patient. So this brought us to another focus group that we have just created together with the WHO. And so there's the AI for Good Summit in Geneva. It happened last year, May 15 to 17. It will happen next year again. And there was a strong demand for standards for health and AI, and we basically created this idea there. And we want to bring AI for health to a global scale. So we would identify use cases that are relevant for public health, and you know, stroke is one of those. We need to understand the data sources. There are varying qualities of data, as you know that. And we would the basic task of this focus group would then to evaluate the performance of AI algorithms. We basically have training data set, test data sets, and figure out how well they are performing. And we would document everything. And at the end of the day, we would basically produce a document with numbers that WHO or other national entities can use to make a recommendation on an AI algorithm. So, the focus group on artificial intelligence for health has been created in July this year. And one of the things that we are addressing is the shortage of health workers. There are millions of health workers missing. And if some people could, well, if you type your symptom into Google, the links you look at, you are practically dead, right? That's at least my experience. So if there's a way to, you know, and there are some apps out there that are working quite well, for instance, Ada, if you had a way to basically, you know, yeah, okay, well, it's probably not going to be the end of my life. If we had a way to be smarter about how we deal with health problems, and particularly using AI, maybe that's a way forward that may help to mitigate this shortage of health workers, in particular in developing countries. So you can see here, it's very bad in Africa, very bad in Southeast Asia, and but also, you know, in this country or in Germany, you can have long waiting times to see certain specialists. And telecommunication offers new solutions. So let me give you one example. On this planet, 1.7 billion people do not have a bank account, but 1.3 billion of them have a phone. So can we use that? Can we leverage this aspect to help them with their health problems? Because if they don't have a bank account, they may not also have good access to a doctor. And so that's why, that's one of the reasons we wanted to create this focus group, Artificial Intelligence for Health. So we are looking at two data mapping problems. One is data to diagnosis. The data sources could be clinical records like SNOMED, CT, or HPO, text, symptoms, description, and images, photos, like photo of your skin for skin diseases, like cancer, videos of behavior. We have a child malnutrition project, microscope, CT, MRI. I mentioned a couple of MRI projects, particularly related to cancer, and X-ray, laboratory results, your blood results, for example, and sensor time series like ECG, EEG, etc. So all these data would then lead to a classification for disease, and the WHO has created this ICD system. ICD-11 just came out, and we want to basically figure out this, well, the mapping is figured out by people who are smart and developing these algorithms, but we want to evaluate how efficient these things are in order then to enable WHO and the national agencies to say everything above this threshold is good for this purpose. And we would then go ahead and provide some degree of quality assurance for this AI algorithm. Then people can use it in practice and actually make it better because there will be more data. So you can basically start the circle in a big way. So our framework actually is planned to be standardized input data sets. We are calling for them. We are confirming the output data through actually a diagnosis given by a medical expert. We will then split the data into public and private and create matrix for comparisons. A false true and a true false in the medical context can be very different in terms of relevance. And then we let the AI algorithms complete and come to a result with regards to their performance, provide a detailed report on the origin of the data, the algorithms, the metric, everything and make this available public, and it's open to everybody. The process is open, the result is open, everything is open, so you can use that. And as a patient, basically decide how well you think this thing is performing. But also these national organizations can also make recommendations based on them. And it can lead to better healthcare for people who don't have access to doctors. It can lead to reduced cost in healthcare, which is also a relevant aspect. And yeah, so we are creating this framework. We are currently working on sourcing of test data. We are working on the gold standards. So we set the benchmarks, and we are also working on a documentation scheme. The interesting thing is we haven't started yet. The first meeting of this focus group is next week at WHO in Geneva. It's open, so if you guys want to overwhelm them with your participation, please go ahead. And you can register for the meeting and come there. Only one thing, it appears to be there's limited space available, so you got to hurry. I think they may have to close it just for logistics at some point in time. Okay, so that brings me to my conclusions. We have used successfully machine learning for video compression, and these video encoding algorithms, compressed video is 80% of the bits on the internet, so it's kind of the most important thing that happens on the internet. And we've been able to use it in multiple parts of the video compression system. And you know, if you save 5% of the bits of a compressed video signal, that means something if it affects 80% of the bits on the internet. We have been successfully using machine learning for communications, and the 5G system is actually relying on it. I don't think we can make 5G work if it's not using machine learning and data the right way. And we have created, therefore, the focus group on machine learning for future networks, including 5G. And the next meeting will be in Japan, in Tokyo, 27 to 29 of November. And last but not least, we have created machine learning for health. In this space, we have created another focus group. And this group has the task to evaluate the quality of algorithms in the space through an open assessment framework so that it can be understood how good this is, and it's not just hyped, it's really on the ground measured. And the first meeting is next week in Geneva, 25 to 27 of September. There are quite a few people I want to acknowledge. Klaus Robert Müller in Berlin. We are working closely together on machine learning, and Wojciech Zamek, he's the colleague who's here for compression, with my colleagues communication, and for health. And I wanted to point out the talk later of Wojciech. He will talk about interpretable deep learning. One of the things that you may recognize is this question, well, yeah, we have this black box and input, output, and it does something, but can we understand what it's doing? And he will basically provide you with an approach to understand how a deep neural network makes its classifications, and how can we know how it makes them. So we will explain it. So yeah, if you have questions, I'll be around for a couple of more. That's the EEG cap back then. Yeah, try everything yourself.